compiler developer. I work on IBM's Scala runtime, and it's called J9. And today I'll be talking about our experiences in designing a robust and scalable interpreter profiling framework. So J9 is a production compiler, so today's talk will probably be a little less theoretical than some of the other talks that you'll see. So to motivate, I'm first going to talk about profile-driven feedback. So profile-driven feedback is a method of driving optimization by using profiling information. And we have found that it can improve performance in dynamic languages by up to nearly 60%. And the great thing about profile-driven feedback in dynamic languages is that it can be transparent to the user. So the runtime can automatically instrument and generate profiling information and optimize without the user having to do a training run. Java, being a dynamic language, is very call and branch intensive. So we found that optimizations like devirtualizing, inlining, and block ordering are important and only get better with the presence of profiling information. In J9, there's two spots that we do profilings. So one is by instrumenting code, which we call JIT profiling, and the other spot is in the interpreter, which we call interpreter profiling. So now let's look at a typical benchmark profile. This is SpecJV 2005, which is a benchmark that's dear to the hearts of many Java virtual machine developers. And on the x-axis, you can see methods, and on the y-axis is a percent CPU time. So as you can see, the first method takes up nearly 20% of the profile. The top 15 take up 80% of the profile, and the remaining 1,000 or so compiled methods only take up 20%. In fact, if you want to capture 98% of the execution time, you'd only need to look at the top 50 methods. And this is what we do in the compiler using profiling technique that's described in Arnold Ryder's paper. So the basic idea of this is you take a method body, you replicate it, you instrument the replicated body, and you have various control flow points back to the original body to help control overhead. So this profiling technique is great for capturing profiling information for applications that have peak profiles, I guess. But the key part to this profiling technique is that you need to recompile the method after you've collected your profiling information. So now I'm going to show you a different profile. This is WebSphere application server running DayTrader. So DayTrader is a benchmark application that simulates a stock trading system, and it's perhaps a lot closer to what customer applications some of our customers run. So as you can see, this profile is radically different than the previous profile. The top 15 methods here only take 13% of the time, and the remaining 9,800 methods take 87% of the time, for an average of 0.009% per method. So if I wanted to capture the same 98% of the profile, I would need to profile thousands of methods and recompile thousands of methods. So that's just simply not possible with the previously discussed profiling technique. So our solution was to do interpreter profiling. J9 is a mixed mode JVM, so this means methods can either be interpreted or they can be compiled to native code. Basically the life of a method starts off as interpreted, and once we've determined that it's sufficiently hot, we will compile it. So by profiling in the interpreter, we're able to solve the mass recompilation issue. But it introduces a new problem. There's overhead to do profiling in the interpreter, and this is mostly felt during startup when most methods are interpreted. And many customers care about startup time. And to give you an idea, startup time can range anywhere from tens of seconds to nearly a minute. So to help further motivate you, here's some of our throughput results with our initial interpreter profiling implementation. So on the y-axis, we have normalized throughput results compared to an implementation without interpreter profiling, and on the x-axis are a series of benchmarks. So I have DayTrader, which I previously showed, and then there's a spec JVM 2000, a subsection of the spec JVM 2008 suite. So you can see on DayTrader we were able to improve performance by nearly 60%, and for the benchmarks from spec JVM 2008, our improvement ranged from just over 20% in compiler.compile to nearly nothing in SciMark. The reason why we didn't get anything in SciMark is because our other profiling technique is able to capture all the information necessary. So now let's look at the effect on startup time. So again, this is normalized startup time compared to an implementation without interpreter profiling. And you can see that again, for WebSphere application server, our startup time regressed nearly 60%. And again, compiler.compile suffered significantly with over 40% regression. And others, the impact wasn't so bad, but 60% regression is in startup time is just simply not acceptable for customers. So now the rest of the talk is going to be mainly focused on the solutions we've implemented to reduce our startup time problem. But before I get there, I'm going to talk a little bit about our interpreter profiler design. So J9 has a VM and a JIT compiler, so we separate the components. The VM is responsible for collecting the data, and it does this by entering the data into a profiling buffer. So here I have two application threads that are interpreting, and then when we execute an interesting bytecode, an entry will be placed into the per thread profiling buffer. When the buffer gets full, the JIT runtime will pause the application thread and then beginning to parse and process each data sample in the buffer. And then it'll enter the sample into the global JIT profiling hash table. So this is a good time to distinguish between the data that comes in the per thread profiling buffer and what's in the hash table. So the records in the profiling buffer are not unique. So if a bytecode is executed 10 times, there'll be 10 entries in that profiling buffer, whereas the entries in the hash table are unique per bytecode PC. Finally, at a later point, when a compile happens, optimizations will consult the data in the global JIT profiling hash table and use it to drive optimizations. In practice, we found it useful to profile 4 types of bytecodes, so branches, virtual calls, switch statements, and an instance of and check cast runtime tests. And we also thought it would be useful to figure out where our overhead was coming from. So there was 4 logical spots for overhead, so populating the per thread buffer in the virtual machine, or the VM, scanning the buffer by the JIT, processing and populating the global hash table by the JIT, or the compilation thread consulting the data. We found that the majority of the overhead came from processing and populating the global hash table. I'll show you 2 other interesting statistics that we've uncovered in doing this. So here's a distribution of our raw interpreter profiling data in a typical buffer. So as you can see, over 50% of the data is branches. There's still a significant amount for invokes, which are calls, and check casts and switches are only a small sliver. And now we can look at the distribution of processed interpreter profiling data. So this is what the data looks like once it's processed and in the hash table. Here, the data is dominated by calls and check casts. There's still a fair segment for branch information, but not nearly as much as before. So this suggests that branches are re-executed many more times than calls. And we'll be using this information later. So now let's get to some optimizations. The first problem we were looking to address was the synchronization overhead on the global hash table. So the global hash table is a global data structure, so some form of synchronization was necessary. We tried initially a lock and then went on to try various solutions, but we found that the issue wasn't a contention issue. The issue was that all these solutions, including lock-free hash tables, use underneath hardware atomic operations. So these operations were expensive and also increased path length. So our optimization was just to remove synchronization. So in order to do this, we had to constrain our hash table implementation. Our inserts now are a carefully crafted sequence of operations. We don't allow deletions. and we don't do resizing. With these constraints, we won't end up with a corrupted data table, but there's still a possibility of losing a sample if there is contention, or essentially a memory leak. But we found from experience that this happens so rarely that it was acceptable to do so. The second problem we looked to address was the buffer processing done on application threads. So when we would process a buffer, the application thread would pause, and it could not make forward progress. So to solve this problem, we introduced a dedicated thread pool to do the processing of the interpreter profiling buffers. This now allowed us to go to an asynchronous model. So when the buffer gets full, we'll just queue it up to be processed, and then get an empty buffer. On multi-CPU machines, we can now hide the overhead from interpreter profiling. And now this exposes more opportunities for tuning. So we can tune the thread pool size. We can decide to drop buffers instead of allocate new ones if we're running low. And finally, we can also delegate buffer processing back to application threads should our buffer processing threads get swamped. In practice, we found that a thread pool size of 1 was sufficient. The third problem that we sought to address was the overabundance of branch entry informations. So if you recall from the two pie charts, we saw that branches take up more space in the buffers, but end up taking a smaller portion of the hash table. And the other thing to note is that branch bias is the important piece of information when you're doing profiling of branches, and frequency is of lesser importance. So knowing this, our optimization was to skip processing branch buffer records in a random fashion. So this would reduce time spent processing entries by reducing the number of entries we're processing. And so this is targeting our largest source of overhead. And by doing it in a random fashion, we're ensuring the branch bias is not affected. Note that this optimization does not improve footprint, because we do expect that eventually that all branches, even though some are being skipped, will end up in the hash table. The next problem that we sought to address is that not all profiling information is used. So some methods are interpreted but never get compiled. So we basically wasted time profiling these methods. And secondly, after a certain point, we've done enough profiling, but we've continued profiling methods, and basically had a glut of profiling information. So our solution was to only profile the last n invocations of the method. This reduced time spent processing entries by reducing the number of entries, and as well we were able to improve the footprint savings of our hash table by nearly 50% by eliminating little used entries. For those worried about resizing, this also reduces the need to resize. And finally, this also biases the profiling information to just before compilation, and hopefully you're doing compilation closer to a steady state. Another interesting problem we came across was an expensive validity check caused by class unloading. So I'm going to talk a little bit about class unloading. It's a Java optimization to reduce memory use defined in the Java specification. So a class can be unloaded if its defining class loader may be reclaimed by the garbage collector. Basically, this means if the class is no longer used, you can unload it. And when you unload a class, you free all the memory associated with that class, including loaded bytecodes. By doing this, you now have possible interactions with interpreter profiling. In particular, your data could have come from an unloaded class, or the processed profiling data could have also been from an unloaded class. So before you use your profiling information, or before you update your information, you have to do an expensive validity check on each entry. So our optimization was to reduce the times we had to do this validity check based on the idea that once you do a validity check for an entry in the hash table, you don't have to redo it unless class loading has happened. So we did this by adding a version ID to each entry and then comparing the entry against the entry's version ID to a global version ID, and we would increment the global version ID when class unload event occurs. So if they're the same, no class unload event has occurred, and we don't need to redo the check. The last problem we came across was the problem of continuous profiling. So some applications would continuously do profiling. So this is common in many flat profile applications. So one example might be an enterprise application that uses like a rules-based system to drive business logic. So they might use the reflection API to generate new classes and new methods, and then shortly throw them away, and it would continuously do this. So this caused a throughput penalty at steady state. Our solution was to stop profiling when we decided that the benefit was small. So when the the interpreter's share of time dropped below a certain threshold, we will just turn off profiling. But this introduces a new problem. If the application undergoes a phase change and starts compiling a lot of new methods, we will be missing profiling information. So we had to implement some sort of phase change detection to ensure that when a phase change occurs, we will turn back the profiler on, so that way when we do a compile, we will be able to use the profiling information for the new methods. So the applications I've shown in this presentation, none of them actually exhibit this behavior, so I won't be showing results for this. And finally, let's look at the results. So this graph shows a cumulative application of each of the optimization techniques I've discussed. So here is normalized startup time. Again, you can see for WebSphere application server, we went from a nearly 60% regression in startup time down to just 2%. So the interesting thing about WebSphere application server startup time is that the class unload optimization had the biggest impact, followed by eliminating synchronization. In general, so the rest of the applications, the eliminating synchronization had the biggest improvement for startup. And now I'll also show you our throughput results. Again, so each bar represents a cumulative application of each optimization technique. So you can see that WebSphere improved by nearly 60%, and we didn't regress the throughput. And you can see, again, for all the other benchmarks as well, there was no regression in throughput. So now a summary. So profile-driven feedback is necessary in any production JVM to obtain peak throughput performance. And some applications have unique characteristics that make interpreter profiling a great solution to generate profiling data. But doing so can significantly degrade startup time. So our optimizations were able to reduce the overhead. So these optimizations being eliminating synchronization on our global data structure, adding separate threads for processing buffers, by skipping processing some branch entries, by only profiling the last n invocations, our class unload optimization, and turning off interpreter profiling. With these optimizations, we were able to reduce an initial overhead of 57% down to a few percent without any throughput loss. Thank you.
Question. Thank you for your presentation. I'm Yoito from Shanghai University. I have two questions. First is, in your talk, you are talking about interpreter profiling, right? So it's mainly about the software profile. And I'm curious, is there any hardware feature used in your profile evaluation? And the second question is, one of your optimization is about skip the processing of the branch buffer. And I'm also very interested about it. I want to ask is, what's the rate you skip the branch because this will cause the this will reduce the accuracy of the profile results.
So to answer your first question, is there hardware profiling techniques?
Yeah. Do you use any of the video profile?
Not in what I've shown today. And so your second question was about skipping branch entries. What's the rate of skipping? I think it's probably somewhere between 15 and 20%, but don't quote me on that. So it can be tuned, basically. And you're right, so you do lose frequency counts, I guess, right? That's the risk. But generally, the big gain, at least in flat profiles, is block ordering. And so there you really more care about branch bias and not the frequency.
Any other questions?
Thanks for your presentation. I'm Feng Li from Chinese Academy of Sciences. My question is, when you talk about problem 4, you use an optimizing technical which only provide the last n iterations of a method. So my question is, could you give us more details about how you choose the values of n, like what kinds of program characteristics you consider?
So it's chosen, I guess, through static analysis, and what we found is that a value of 1,000, like basically, so it depends on when you decide to compile methods too. So if you're using sort of a count-based way to determine when you compile a method, it depends on your initial count too. So if you're compiling a method after 3,000 invocations, you don't need to profile all 3,000 of those. I guess it depends. Like, there's a lot of heuristics involved in picking the n, but right now I can say it's near 1,000.
So the default value is 1,000.
Yeah.
Thanks.
All right. One last question, maybe that I have. You mentioned that after you reach a stable phase, you discontinue any more profiling for methods. Now, that can take a while. I would imagine this doesn't contribute much to the startup time before you reach that. And my second part is...
Yes, right. So that optimization was for reducing throughput penalty from interpreter profiling. Sorry, I should have been a bit more clear on that.
Okay, but my follow-on was, you alluded to the fact that you actually have phase change detection. How do you actually do that?
It's based off of class load rate. So if you start loading a lot of new classes, we'll likely turn the profiler on.
All right, but if inputs change and you have branch-based differences, you wouldn't detect them?
Yeah, I guess that's a different type of phase change.
All right, that concludes the session. Let's thank the speaker again.